I would like the first promoter, Professor van Brummelen, to start the opposition.
Dank u wel, meneer rector. Geachte promovendus, could you please explain to us, the committee and in the audience and the people online, in at most 10 minutes, the contents of your thesis work?
Ogereda promoter, I would kindly answer your request with a short presentation. Simulation-based engineering has transformed industry by complementing research and development with powerful computer simulations. It allows us to optimize products, reduce costs, and shorten time to market. Its impact on the technology and the economy has been increasingly profound thanks to the evolution in computing capabilities, the emergence of data science and AI tools, and the development of sophisticated data analysis softwares. However, while it's mature for single physics problems, its potential in multi-physics applications is still not sufficiently exploited. Integrating different physics, such as fluid dynamics and structural mechanics, poses unique educational, technological, and organizational challenges. The limitation of single physics have become increasingly evident as researchers tackle complex problems in fields like hydrodynamics, aerodynamics, and hemodynamics. Moreover, there is still a significant knowledge gap between industry and academia in applying these complex simulations. For all those reasons, my PhD was part of a broader European initiative to bridge this very gap. My research had focused on a specific complex multi-physics application, a microfluidic pilot-operated control valve, or POCV for short. In this valve, a pilot region controls and actuates a main larger valve using shape memory alloy actuation mechanism integrated within an electronic device. Its development intends two modes, the proportional and the on-off mode, making it an attractive option for tasks like dosing, dispensing, and mixing. This tiny, high-tech component is critical in fields requiring precise fluid delivery, from medical diagnostics to food and beverage industries. However, while this valve is working perfectly fine in the on-off mode, it failed completely under the proportional control mode. It experienced severe vibration, making it unstable and unusable for its intended purpose. This raises the following questions. Where does this vibration stem from? And can we use numerical methods to address it? To answer this question, I set a twofold objectives. Objective one consists of the development of suitable numerical methods that can faithfully simulate the fluid structure and contact interaction within the POCV. The objective number two consists of leveraging these numerical methods to understand and potentially mitigate. Now, first, let's clarify the difference between the on-off and the proportional control. You see, the principle is quite simple. As the pilot valve opens, it releases pressure, creating a pressure imbalance between the main and pilot regions, thus opening the valve. For the proportional control, a continuously varying signal dynamically adjusts the flow as desired by the user. Hence, the valve can occupy any position between the fully open and the fully closed set points. For my investigations, I developed a numerical model using a method called the Partitioned Fluid Structure Interaction Approach, or FSI for short, within the ANSYS software suite. This came with big challenges, as this method had to account for the strong coupling between the fluid flow and the large structural deformation, as well as the contact between the membrane and the valve seat, not to mention the high computational cost associated with simulation runtime and the post-processing of hundreds of giga of data. My model first validated what was observed experimentally. In the on-off mode, the valve worked flawlessly, and my computational results were aligned with experimental data. But when I simulated the proportional opening, the failure was immediate. As soon as the valve tried to open partially, it started to oscillate violently. Simulation could see what experiments couldn't. The instability was caused by a Venturi effect in the narrow gap of the partially open valve. To put it simply, as the fluid rushes through this narrow gap, its velocity increases, creating a sharp pressure drop. This low pressure at the vicinity of the valve seat sucks the membrane back down, closing the valve. The pressure then builds up again, pushing the valve open, and the cycle repeats, leading to this self-sustained vibration. With this understanding, I proposed a new design of the valve. The main idea was to reroute the flow in such a way that instead of flowing almost tangential to the main membrane, the inlet is now perpendicular to it. This change, alongside the change in the valve seat geometry, were intended to mitigate the vibration. After several trial and error procedures, I improved the design and ran similar FSI simulations. From a computational perspective, the results were promising. The vibration were gone, but the overall performance of the valve has also improved. During this process, I kept running into a puzzle in numerical issue. You see, the partition approach that I use is based on the Dirichlet-Neumann coupling scheme, which stipulates the continuity of motion and the continuity of traction across the fluid structure interface. This coupling scheme is known for its limitations for strongly coupled problems, but it also tends to fail for large fluid to solid density ratios, which require stabilization techniques for conversions. Although we addressed all these limitations, my simulations kept failing when they shouldn't have been. This led to a deeper investigation of the numerical methods themselves. Such an investigation became an integral part of my thesis and led to a significant contribution to the field. We discovered that the Dirichlet-Neumann coupling scheme, which is used by most FSI solvers, introduces a hidden artifact in the nearly closed fluid configuration. To explain it simply, the high flow resistance in the narrow gap acts like an artificial damping force, which is not physical, but can deteriorate the entire calculation. Our investigation suggests that this added damping effect is proportional to the time step size, is proportional to the flow resistance, and is inversely proportional to the solid mass. I believe that this finding is crucial for the FSI community, as it provides for the first time the last missing piece regarding the limitations of the Dirichlet-Neumann coupling scheme. That is, I believe in the future, once addressed, FSI problems involving contact and nearly closed fluid domain could be solved. To summarize, my research had made 4 key contributions. First, I developed a design tool using numerical FSI method to simulate an industrial multiphysics application. I determined the physical mechanism behind the valve instability. And based on this insight, I proposed a new, computationally, I proposed a new improved design of the valve. And finally, we discovered and mathematically characterized the added damping effect. Hooggeleden promotor, I hope you're satisfied.
Geachte promovendus, thank you very much. Yes, I'm satisfied with your answer.
The Eindhoven University of Technology appreciates it very much when experts from abroad want to participate in PhD defense committees. We are therefore very much obliged to Professor De Tulio from Polytechnic Institute of Bari, to Dr. Conti, University of Pavia, Professor De Grote from the University of Ghent, Professor Berr from the University of Aken. And to complete this round of introduction, on my right side is the first promoter, Professor van Brummelen. On my left side, Professor Kurte from TUI as well. He serves as the secretary of this committee. And on the very left, Professor Riccio, also University of Pavia, and he serves as the second promoter today.